In this video, we will be exploring the idea of a derivative. But before we do that, we're going to use our knowledge of the difference quotient to determine the slope of a tangent to a curve at a very general point. So, our first example, a little warm-up. Use your knowledge of limits to determine the slope of the tangent to the curve f at x equals x squared when x equals a. So we're not given a specific point here, we're given this general coordinate of a. But I'm going to use the same idea as I would with the difference quotient when I'm trying to find the slope of a tangent at a specific point. So I'm going to start off with f at a. F at a would just be a squared. And then to that value of a, I'm going to add h being the horizontal distance between these 2 points. And we're hoping that horizontal distance will approach 0. So that will be a plus h squared, which remember just means a plus h times a plus h. So that will simplify to a squared plus ah plus ha. So that's 2 ah's plus h squared. Now I'm ready to find the slope of the tangent. So the slope is going to be the limit as h approaches 0 of y2 minus y1, so this minus this, a squared plus 2ah plus h squared minus a squared, all over a plus h minus a, but the a's cancel out, so we're just left with h. And now if we look at our numerator, a squared minus a squared is 0, and we're just left with these two terms. And those two terms have an h in common. So I'm going to factor it out. And when I factor out an h, I'm left with 2a plus h all over h. And the h's cancel out. And we're left with the slope being the limit as h approaches 0 of 2a plus h. And now I have no problem substituting 0 in for h. So that would be 2a plus 0, which is just 2a. So this here is an expression that represents the slope of any tangent line on the function x squared. All I'd have to do is replace a with whatever x value I'm looking for, which is what we're going to do in the next example. Determine the slope of the tangent when x equals -4, 0, 3. Okay, well, instead of me doing the difference quotient 3 times, I'm going to use this general slope. So 2 times -4. The slope when x is -4 is -8. The slope when x is 0 for the tangent line is 0. The slope when x is 3 is 6 for the tangent line. So this is very nice because I'm cutting down on time because I'm not doing the difference quotient 3 separate times. I do it once and then I can plug in whatever value I want in. Now this here is actually called the derivative. This general expression for the slope of the tangent is the derivative of the function. So this leads us into the first principles of derivatives. So the derivative of a function represents the slope of that tangent at any point x. So in other words, it's the instantaneous rate of change at a specific value x. Now we have two different notations that we can use. The first is the Lagrange notation, and it connects really nicely to function notation because if we have the function f at x, we can use f prime of x as our derivative. So there's just a little apostrophe after the f. And if the function we were given was written as y equals, then we can write y prime for the derivative. And then we also have the Leibniz notation for the derivative, and that identifies the variables that are involved. So the derivative of y is represented by dy dx. And please note that dy dx is not a fraction, it is one quantity. So if I was given f at x and I wanted to use this Leibniz notation, I would write df at x over dx, something like that. So what is the first principles? It's the difference quotient but using a general variable. So the derivative of f at x, so f prime of x, is the limit as h approaches 0 of f at x plus h minus f at x all over h. So the only difference between this and the difference quotient is that we're not subbing in a specific value for x while we're evaluating our limit. We keep it as that general variable, which gives us the derivative. So let's determine the derivative of the following functions. Our first one is f at x equals the square root of 3x, where x is greater than or equal to 0. Okay, so I have f at x already. I do need f at x plus h. So that would be the square root of 3 times x plus h. And that would be the square root of 3x plus 3h. So instead of me writing m for slope, I'm going to show that I am finding that derivative, that general slope of the tangent. So it's the limit as h approaches 0 of the square root of 3x plus 3h minus the square root of 3x all over h. And like normal, when we do see that radical, hopefully we're thinking about the conjugate. So I'm going to multiply the numerator and denominator by the square root of 3x plus 3h plus the square root of 3x. And now let's clean this up. The limit as h approaches 0, well, the square root of 3x plus 3h times itself will just be 3x plus 3h. Then the outsides and insides cancel out. That's the whole point of the conjugate. Minus the square root of 3x times itself is 3x all over h times the conjugate. And again, I'm not going to be distributing that h in because I'm hoping things will cancel out. So if I look at my numerator, 3x minus 3x is gone because that's just 0. So we're just left with 3h in the numerator. And then, because of that, h divided by h is 1. So we can cancel those out. And we're only allowed to cancel those out because the 3x's collected to 0. If they didn't, it would not be okay to cancel out the h's. So the limit as h approaches 0 of 3 over that conjugate. And now let's substitute 0 in for h. So I have 3 over the square root of 3x plus 3 times 0 plus the square root of 3x. Well, 3 times 0 is 0. So for that first radical, I just have the square root of 3x. And I have it twice in the denominator. So that'll just be 3 over the square root of 3x. Now, if you wanted to take an extra step here and multiply top and bottom by the square root of 3x to eliminate the radical in the denominator, you're more than welcome to. And then I can cancel out those 3's. And we can have this as our derivative. And I will add an extra note here that x has to be greater than 0, which is a little different from f at x, which was greater than or equal to 0. I want to be greater than 0 because of the radical. We can't square root a negative, but I want to be greater than 0 and not equal to 0 because I can't have my denominator equaling 0. So there we are. There's our derivative. Next, we're going to try a rational example. So we have g of x equals 2 over x minus 3, where x does not equal 3. Okay. I'm going to figure out g of x plus h, which I don't have to do this as an extra step. I like to do it sometimes in case there's something for me to clean up. In this case, there isn't. So I'm going to go to finding my derivative, g prime of x equals the limit as h approaches 0 of 2 over x plus h minus 3 over 2 over x minus 3 all over h. So I see this fraction within a fraction, which is making me think of a common denominator. So I'm going to multiply this first fraction by x minus 3 and the second one by x plus h minus 3. So we have the limit as h approaches 0. I'm going to write that common denominator. Here it is. And now I'll distribute the 2 in to x minus 3 just to clean up a little faster. And for the second one, I'm not just distributing the 2 in, I'm distributing negative 2 in to those 3 terms in the bracket. So we'll have minus 2x minus 2h plus 6. And then instead of putting this fraction all over h, I'm going to write it as divided by h, or jump straight to times 1 over h, the reciprocal, because that's how we divide fractions. And now I'm just going to clean up. 2x minus 2x is 0, negative 6 plus 6 is 0. So we're left with negative 2h over the common denominator times that reciprocal of h. And now those h's cancel out nicely. And I will also go in and replace h with 0 because now I can substitute that in. So I'll have x plus 0 minus 3 times x minus 3. So I have x minus 3 2 times, so I can write this as x minus 3 squared. With the little restriction, x cannot be 3. And there we are, 2 derivative examples, one for a square root and one for a rational function. Now let's apply this to a typical calculus question. Find the equation of the line that is tangent to the curve f at x equals x squared minus x at x equals 2. Now, before I would do this using the difference quotient, this time I will use first principles just to practice finding the derivative first, that general slope. But of course, you could use the difference quotient here. So we have f at x. I want f at x plus h as well. So that's going to be x plus h squared minus x plus h. I'm careful here, I'm putting it in brackets. And I'm going to clean up. That's going to be x squared plus xh plus xh. So 2xh's plus h squared minus x minus h. Okay, that's as clean as we can get it. So the derivative is going to equal the limit as h approaches 0 of the expression we just got minus f at x itself all over h. Now you can start canceling things out here if you would like, because x squared minus x squared cancels out, negative x minus negative x cancels out. But if it's hard to visualize that, go ahead and distribute that negative in. And you're left with x squared plus 2xh plus h squared minus x squared plus x all over h. So x squared minus x squared gone, negative x plus x gone. Everything else that we're left with, 2xh, h squared, and negative x, they all have an h in common. So I'm going to factor that out. And I have 2x plus h minus 1. And this allows us to cancel out the h's. And now, if I replace h with 0, I have 2x plus 0 minus 1, which is 2x minus 1. Here is the derivative of that quadratic. And now, if I want the equation of the tangent line at x equals 2, I need the slope when x equals 2. So my slope is just the derivative of f at x when x is 2. So that's 2 times 2 minus 1, which is 3. So we have y equals 3x plus b. And we don't actually have a point to plug in yet, but I can find it. I'll just replace x with 2 in the actual function itself to find the point on the parabola. And when I plug in 2, I also get 2. So we can use the point 2, 2 to find our y-intercept. So that's going to be 2 equals 6 plus b. So b must be negative 4. So here's the equation of this specific tangent line when x equals 2. And finally, finally, we also have, instead of a tangent line, we can also find the equation of the normal. And as a reminder, the normal to a graph, let's say f at x, is the line that is perpendicular to the tangent line at a specific point. So let's find the equation of the normal to the graph of f at x equals the square root of x plus 4 at x equals 0. Now, of course, I can use my difference quotient to find the slope of the tangent line when x is 0, but I'm just going to find the derivative to practice that skill and then go from there. So f at x plus h will equal x plus h plus 4. All right, so our derivative will be the limit as h approaches 0 of the square root of x plus h plus 4 minus the square root of x plus 4 all over h. And I see those radicals, so I'm thinking conjugate here. Top and bottom. And when we simplify, in our numerator, we'll be left with x plus h plus 4 minus x plus 4. And be careful to put the x plus 4 in brackets, because that subtraction or that negative has to distribute into both. Okay, and we can distribute that negative in, or we can cancel out while we think ahead. So x minus x is gone, 4 minus 4 is 0. So that we're just left with h over h times the conjugate. So because my numerator is just an h and the h is outside of that bracket, we can cancel those out as well. So now, actually, I'll just replace h with 0. We have 1 in our numerator, and in our denominator, we have x plus 0 plus 4 plus the square root of x plus 4. So that's us having x plus 4 twice. Now you might want to multiply by the square root of x plus 4 to eliminate the radical in the denominator here, but because the question isn't to find the derivative, it's to find the equation of the normal, I'm just going to go straight to finding the slope of the tangent. So the slope of the tangent is the derivative when x is 0, and I'm just going to plug straight in, and if I still have a radical in the denominator, I will rationalize it later. But I won't, because 0 plus 4 is 4, the square root of 4 is 2, times 2 is 4. So that's the slope of the tangent line, but we want the slope of the normal. So we need to take that opposite reciprocal, and we get negative 4. So y equals negative 4x plus b. Now, we never found the actual coordinate in our function, but no problem, we can do that. I'll quickly find f at 0, and the square root of 4 is 2. So we can use the coordinate 0, 2. And luckily, 0, 2, well, that's already the y-intercept. So I can go straight to my equation. Y equals negative 4x plus 2 is the equation of our normal. Now, final quick note here. There are certain parts of certain functions that are said to be not differentiable, and that's when the derivative does not exist at a specific point. And we have 3 scenarios. When we have a cusp, so you'll see this curved portion that just changes direction really rapidly, or we could also have a kink in a function, and that would be something like when you have an absolute value function. So it's 2 lines and the direction just changes very abruptly. So in those scenarios, they are not differentiable. Or if you have a vertical tangent line, like in the second example, or some sort of discontinuity, like a jump, for example, that is depicted in that third example. And that's it for finding the derivative using our knowledge of limits and first principles.